Good afternoon. In some bird species, the males and females are visually easy to distinguish because they're different colors. In other species, like blue jays, they're the same color. I'm going to tell you more about that in just a second. Thank you. In some bird species, like cardinals, the males and females are visually easy to distinguish because they're different colors. In other species, like blue jays, the males and females appear identical to humans, but not to other blue jays. This is because birds, unlike humans, can see ultraviolet light. And the plumage of male and female blue jays reflects ultraviolet light quite differently. So when blue jays look at each other, they see something that humans cannot. They are seeing colors that humans have never experienced. In fact, if blue jays could have named themselves, they would probably have called themselves ultraviolet jays. So would we say that male and female blue jays are different colors? Well, it depends on whether we're defining color based on a feature of the object, like what wavelengths of light an object reflects, or based on a feature of the perceiver, like what humans can see. So today, I'm going to be unpacking color vision to help us understand the beauty and complexity of this perceptual process. Color can be described as a visual experience based on the electromagnetic spectrum. The light that humans can see ranges in wavelength from about 400 to 700 nanometers. And this light that's visible to humans is just a narrow slice of the electromagnetic spectrum. If we could see shorter wavelengths, we would be like our blue jay friends, seeing into the ultraviolet. And if we could see longer wavelengths, we could see infrared light, body heat, all the way out to radio waves. Those are all kinds of light. Now, because certain wavelengths are associated with certain colors, it might be tempting to think that we could define color based just on the physical properties of an object. Maybe what I mean when I say that object is yellow is that object is reflecting light at around 580 nanometers. So first, we're going to test out this idea that we could define color based on physical features of an object. This works well for some yellow objects. So the lovely yellow slice of the rainbow that you see in the middle there is indeed refracted light at about 580 nanometers. The graph here is showing wavelength along the bottom, and the height corresponds to brightness. So a pure yellow light source, like a yellow laser, is indeed reflecting or emitting a very narrow band of wavelengths, right around 580 nanometers. Okay, what about this? Would you call this yellow? Unfortunately, this does not fit our definition of yellow as a 580 nanometer wave. The light that you are seeing here contains little to no 580 nanometer light. The projector that's creating this over your head is a laser projector that has 3 light sources that correspond to red, green, and blue. The experience of yellow that you're having is because the projector is simultaneously presenting red and green light. Mixing light follows different rules than mixing paint. When we combine red and green light together, it leads to an experience of yellow. So this is a way of creating a yellow experience that has nothing to do with 580 nanometers. All right, what about the folks at home watching this on phones or computers? What kind of light are you seeing? The screen you're watching this on also contains 3 light sources that are LEDs that again correspond to red, green, and blue. No yellow. If you take a magnifying lens on a camera and zoom in closely, you can see that now the experience of yellow is created by an array of red and green lights that are packed really closely together. They are packed so closely together that your eye cannot resolve the difference between them, and the light ends up getting blended the way that it does with the flashlights. So now we have 3 ways of making yellow: 580 nanometer light, red and green light simultaneously, or red and green light close together. But these last 2 are like unnatural digital objects. What about like real yellow objects out in the wild? Most natural objects that appear yellow to us are reflecting a really broad range of wavelengths. So like a lemon, for example, would reflect light across almost the entire visible spectrum. And it's interesting to note that this is reflecting more light in the red region than in what we would typically call yellow. So So you can start to see the problem with defining color based just on wavelength. There are so many different sets of wavelengths that all lead to the same perceptual experience. All right, let's make it even worse. I invite you to stare at the white plus sign in the center of the screen. Try to keep your eyes really fixed on that point and blink and move your heads as little as possible. While you do that, I'll tell you that staring at something for a long period of time leads your eyes to adapt so much that it can actually change what you see in the future. So this leads to perception in a new way, not based just on the wavelengths that are currently present, but based also on wavelengths that were previously present. In just a minute, I'm going to change what's on the screen, but I want you to keep your eyes fixed on that white plus sign. Ready? This is a black and white image. Do you want to do that again? Yeah, okay. So when you're looking at the sunflowers that now appear to be blue, the light-sensitive cells in your eyes are adapting and changing. Later, when we switch to looking at something gray, you're going to end up seeing the complementary color of blue, which is yellow, because the blue-sensitive cells in your eyes have reduced their response. Ready? All right, so this is now an entirely different way of getting a yellow experience. We are seeing an object that under normal circumstances we would call gray, but it looks yellow if it's viewed immediately after something blue. All right, so to summarize, we can have yellow experiences from 580 nanometer light, from red and green light that is on top of each other or close together, from broad spectrum of light peaking in the red, and even from something that normally looks gray. So this really challenges the idea that color can be defined based on wavelength alone. We have all of these different sets of wavelengths, but they all lead to the same perceptual experience. Indeed, there is no red in 700 nanometer light, just as there is no pain in the hooves of a kicking horse. Looking at the wavelengths is not enough. We have to think about how those wavelengths interact with our anatomy. So what do all of these have in common? Why do they look the same to us if they're so physically different? The answer has to do with the fact that despite the fact that different wavelengths are coming off the objects, they all lead to the same pattern of response within our eyes. So when light makes contact with the eye, it's translated into a set of electrochemical signals by specialized cells that are specifically receptive to short, medium, and long wavelengths of light. When that pure yellow light source makes contact with the eyes, it leads the medium and long wavelength sensitive cells in our eyes to respond at equal levels. When the red and green light is presented to our eye, that also leads the medium and long wavelength sensitive cones to have an equal response. So despite the fact that the wavelengths coming to the eye are different for all of these stimuli, the signals that the eye sends up to the brain are the same for all of them. Our eyes cannot tell the difference between these. So maybe instead of defining color based on wavelength, we can define it based on these signals that are coming out of our eyes. Perhaps what I mean when I say that object is yellow is that object is leading to a particular pattern of electrochemical changes in the cells leaving my eye and heading up to my brain. So let's test out this theory now instead. Okay, what color are the bananas? Thank you, you're doing great. Okay, yellow, but like they're under a blue light source, yeah? All right, however, if we look at some isolated sections of the bananas, so you can't see anything about the ambient light, what you'll notice is that the light coming off the screen could actually best be described as gray. Yeah, there is no point on the screen that you would call a satisfying shade of yellow if you looked at it in isolation. So what that means is that our eyes are sending signals up to our brains associated with gray, not with yellow. Do you know what we call that? That's bananas. All right, so if our eyes are sending signals associated with gray, then why do we have the perceptual experience of yellow? It seems that our visual system is combining the signals from our eyes with our knowledge of the overall lighting. So we know that things look different under blue light than they normally do. They look bluer. And so we're trying to compensate for that blue light to understand what the object is underneath. We are, in fact, not seeing objects as they actually are. We are seeing them as we predict they would look if we could see them under neutral lighting. And your visual system is exactly right, that if you were to pull that blue light away, the bananas would be a satisfying shade of yellow underneath. So this is something that the visual system has to do all the time. Slides are not advancing. There we go. Okay. The light that reaches our eyes changes dramatically based on the nature of the ambient light. And so this means the visual system has the very challenging task of trying to understand what an object is, despite the fact that the wavelengths reaching the eye are quite different. It would be a very confusing world indeed if we thought that objects themselves were spontaneously changing color when we moved them from daylight into shade into artificial incandescent lighting inside. So the visual system has to be able to see past this to understand the object underneath. The visual system is not a very good light meter, but that is not the purpose of having a visual system. The purpose of being able to see is to help us predict what's out there in the world. So we can't define light just based on, or we can't define color just based on wavelength. We can't define it based just on the signals leaving the eye. Instead, color appears to be created in our minds to help us predict what's out there in the world. Now, with our original gray bananas, we could all agree that the ambient light was bluish. But what would happen if we couldn't agree? In 2015, an image of a certain dress became an instant viral sensation. The internet was collectively amazed that people could look at an object and see it differently. Some people swear the dress is black and blue, others argue that it is white and gold. But if we again look at a couple of isolated chunks without the context, what you see is that in isolation, neither explanation seems quite right. I would better describe these as kind of brownish and kind of slate gray, cornflower bluish. So we can all agree on that, right? Okay, so if we agree about the colors in isolation, why do we disagree about the object itself? The debate seems to come in part from disagreement about the nature of the ambient light in the photograph. So this isn't anything about the dress. This is about the light the dress is in. Have a look at the top corner of the photograph and think to yourself whether that looks to you like natural light, like sunlight, coming in maybe through a shop window behind the dress and casting the dress into shadow, or whether you think the dress is in bright, incandescent light lit from the front. People disagree about this in ways that affect what they perceive. So let's focus on this cornflower blue chunk in the middle and talk through two different ways of interpreting that light. When we look at the dress, we all agree that there is something bluish happening here. The debate seems to be whether that blue tint is coming from the object itself, that is the fabric of the dress, or whether it's coming from the light. So one way of achieving this cornflower blue would be to have a white object that is under a blue light. So akin to natural daylight coming behind the dress, backlighting it, and casting it into shadow. Another way of getting the same cornflower blue tint would be to have a dark blue object that is in a bright white light, akin to having a bright, unnatural, incandescent, like artificial light from the front. So put another way, if you assume blue light, then the dress looks white. If you assume white light, then the dress looks blue. The image, the quality of the image is pretty low, and the lighting really is ambiguous. So both interpretations are possible and would lead to the same cornflower blue shade reaching your eye. Here's another demonstration. If you assume blue light, the dress looks whiter. If you assume white light, the dress looks bluer. When in fact, what reaches your eye is the same. It's not entirely clear why we make different assumptions about the nature of the light, but it might have to do with individual differences in how much natural light we typically see or have recently seen. So when we look at the dress or any object, we are combining the signals that we're getting from our eyes with the context that the image is taken in. We are basically trying to reverse engineer what we think is out there in the world based on the limited and often ambiguous information that reaches our eye. Examples like the dress are exciting because they remind us that color lives in our minds, not in external objects. We each walk in our own perceptual worlds, and we see things differently from one another. It is impossible to ever inhabit someone else's perceptual world and see things the way that they do. The closest you can get is to listen when they tell you about their perceptual experiences. It is like getting postcards from a place you can never visit. So, variability in perception doesn't have to be a source of contention. I'm not going to tell Blue Jays they're seeing things wrong because they see it differently than I do. Perceiving things differently from one another isn't something to argue about. It's something to marvel about. Thank you.